All right, let's learn about light waves. So, to set up this science notebook page, you just need one page, and again, we're going to do something very similar to our sound waves page. With light waves, we're going to define the light waves. We're going to look at what changes color and what changes brightness when we look at light waves. All right, let's dig in. Light waves, these do not travel as longitudinal waves. These ones travel as those other ones that were called transverse waves. So a transverse wave, if we remember, if we go down here to our point of propagation, a transverse wave is going to go up and down, and this is typically how we see them. Ooh, that was not a good wave. Let's try again. Okay, that's a decent wave. So the wave looks more like rolling hills. So what this means is that the motion of the wave is perpendicular this time to the point of propagation. So what that means is that the wave at the point of propagation, if it's going left to right, then the wave is going to travel up and down because that would be perpendicular to the left and right direction. So we have motion in the up and down direction. So this would be like if you and a friend were holding on to a jump rope and you were to shake your arm up and down, you would end up creating a transverse wave. So let's dig into what happens when we change the wave attributes of a light wave. So if we want to change the color of light, this is pretty wild. You can buy an LED light these days that can turn from red to orange, to yellow, green, blue, indigo, violet with one bulb. That's just your single bulb. You don't need a new bulb for each one because that LED is actually able to change the wavelength that it is emitting. And when we say it's emitting, that means that it's producing or it's letting off. If this is my little LED light, it's letting off this wave. So I should draw it like this to show these waves are coming off of the LED. Well, we can change the wave that's coming off of the LED to get different colors of light. And so to begin with, you need to first write Roy, R-O-Y-G-B-I-V. Roy G. Biv is kind of the way that you can remember the colors of the rainbow, with red, orange, yellow, green, blue, indigo, violet happening in that order. And it's really important to know this order because it all relates back to wavelength. So write out the letters, write the words of the colors, and then draw yourself some wave axes here that you have a horizontal line that you can draw some waves on. Now, in order to make sure that we draw these waves appropriately, I'm going to draw some little hash marks here on my graph so that I can make consistency in my waves. So first, I'll mark a line at the halfway mark, and then I'll go to the left and mark a halfway mark from in between those two, and then I'll mark a halfway mark from the middle to the end here at the end. All right, let's draw some waves. So a red color wavelength is going to be a long wavelength, and so this wave is going to be something like this. Orange would be if you squeeze the wavelength down just a little bit, you're going to end up with some orange light. If you squeeze it even more and make it even smaller, you end up with some yellow light. Green light, as you can probably guess, is a shorter wavelength. Blue is an even shorter wavelength. Indigo, even shorter, and violet is the shortest color wavelength. Okay. So what that means then, the reason that ultraviolet light is so bad is because it's got such a high frequency or a short wavelength that it can actually damage our skin. And that's why we get burned from ultraviolet light. All right, and we don't get burned from infrared light because infrared light is even longer wavelength than red light is, and that's actually how we feel the heat from a fire. So we don't get burned from the heat in a fire, we just get warmed by it because it's a really long wavelength, and we don't see that heat because it's not quite red. It's not a color yet. It's not short enough to actually produce a color, but it's still very similar in the stuff that makes it up. All right, let's look at the brightness of a light. So when you wake up in the morning, you do not want to get blinded by the bathroom light. And so if you had the ability to change the amplitude of your light bulb, you could reduce the brightness. And you might have a dimmer switch that actually does this for you. So again, just like with our sound wave, we're going to draw a small amplitude wave here. And this small amplitude wave is going to be your amplitude is going to be we'll call it a dim light. And if I then increase the amplitude, I'm not going to change the wavelength because I want the same color of light here. But if I increase the amplitude, I now have a large or a high amplitude. And this is going to be very bright. Not a fan of that in the morning, that's for sure. So brightness is just simply changing the amplitude. Again, if we look at the wavelengths, let's take a look real quick. Wavelength is from crest to crest. The wavelengths of both of these waves are actually the exact same. So the color would be the same because wavelength is color. The brightness is different because you have a much higher amplitude or a much lower amplitude. All right, so to finish off here, we're going to just take a look at something because light is something that we all know as humans. We understand it. It makes sense because we see it all the time. But light, I'm going to put air quotes or I'm going to put real quotes around this word light because it's actually only one of the 7 types of electromagnetic radiation. Now, electromagnetic radiation is basically a word that we can break down. Electromagnetic just means that we have electric and magnetic forces that are acting together at the same time. And then radiation is just simply the emission of energy through space. So radiation, you can get radiation in a lot of different ways, and that's just the energy's moving through space. And so electromagnetic radiation is when we have this electric and magnetic force that is traveling through space. So if we look at the electromagnetic spectrum, the reason that light, I put in air quotes, is because this visible portion is what we would call light. So we could break down the visible and have all of the colors of the rainbow in the visible light spectrum. And that's why ultraviolet is right next to the violet portion of the visible light spectrum, and infrared is right next to the red section. And so as we increase the wavelength, we go further and further down to the left. Radio waves have the longest wavelength, then microwaves, which heat up the water in our food that make it warm. Then we have infrared, visible, and then we go and we start squeezing that wavelength down closer and closer and closer. We can turn that violet light into ultraviolet light. If we squeeze ultraviolet light down even more, we can get X-ray electromagnetic radiation. We squeeze that down even more, we can get gamma rays. And so if you want to know what the actual wavelengths are, if these are the wavelength of a radio wave is like the size of a building. Huge. A microwave is like the size of a person. Infrared light is something like, the wavelength is something like the size of an ant or a pinpoint. Visible light is like the size of bacteria, and you can see here's the visible spectrum right here. There's all of our colors. As we start to squeeze it even more, ultraviolet light is the size of a molecule. That's why it can cause burns on our skin, because it actually disrupts the molecules in our skin and causes them to break down and be burned. X-rays can affect all the way down to our atoms, and that's why if you get too many X-rays in your life, you could develop cancer, because you're going to start to affect the atomic composition of your body. And gamma rays are what you get, or what can definitely cause cancer, because they get all the way into the nucleus of the atoms. They're so small, the wavelengths, that it disrupts the nucleus of the atoms and it can cause it to break apart. So there you go. You can see that yes, light, we can call it a light wave, but really the electromagnetic spectrum is much more different than that. So it's like having a box of Crayola crayons with 64 crayons and only being able to write with like 3 of those crayons is like using this idea of light. But if you want to write with all of the crayons, all 64 of them, then you need to embrace the full electromagnetic spectrum. Well, there you have it, ladies and gents. This is how we have all of our technology in our world, is with the power of the electromagnetic spectrum. So time to then look beyond light. Get it? All right, see ya.